Hello, this is video 30, and I want us to look at a possible solution to a problem that just arose. Depending on the order of insertions, we could lose our nice order log base 2 event searches in our binary search tree. It could degenerate, I like using that word so I say it a lot, degenerate into order in searches. So let's use a balanced tree. Here's one type of balanced tree. One type of self-balancing, but that's longer to write, balanced tree, B-A-L-A-N-C-E-D, tree. I'm trying real hard not to mess with the keys up there. This one's called a 2-3-4 tree. And it is as exotic as its name suggests. It's a weird little thing. A 2-3-4 tree, I'll just keep going with that line. This one has internal nodes with 1, 2, or 3 data items. 1, 2, or 3 data items. I'll call them, well, no, I'm not going to call them values because they will be value types, of course. Data values. And if you thought that was weird, 0, 2, 3, 4, or 4 child nodes, also known as children, has internal nodes with 1 or 2 or 3 data values stored in them. And hanging off the bottom, instead of just left and right child, we now have either 0 children, or we leap up to 2 children, or 3, or 4. And wait, there's more. Emphasize and. All internal nodes with no children all internal nodes with no children, also known as the frontier of the tree, the bottom edge, the leading edge. All internal nodes with no children are at the same level in the tree. What does it mean to be at the same level? It means the path from one of those nodes across the bottom to the root is the same for any of those nodes across the bottom. In other words, if you start at one of these nodes at the bottom of the tree and count how many arcs it takes you to get back to the root, it's going to be the same for every single node across the bottom of the tree. And if that's not balanced, I don't know what is. There are cases of nodes. Nodes can look different ways at different times depending on what's going on in the structure of the tree. Node case number 1, and I'm only doing the internal nodes. The external nodes are still going to be represented with 0 pointers. So I could have a node that looks like this. Even the picture of the node got weird all of a sudden. Since we could have up to 4 children, I need 4 pointers across the bottom. They're not left and right anymore. They're child 0, 1, 2, and 3. And 3 data items. Look at that. All of that is just a skeletal representation of a node in one of these trees. In this case, I'm going to say we've only got 1 data item, which I'm going to call D sub 0 to be generic about it. And to the left over here, we would have all the nodes with labels, in other words, data values, labels less than D0. What do we have in the second pointer? Second child pointer will be all the labels that are greater than Z0. Now, if you can pierce through the weirdo look of the node and the notation and everything, you'll think, well, you know what? That is a binary search tree node. And you would be exactly right. We've got data in the node, and to the left are all the nodes that have data that are less than D0, where D0 is the data in the node of interest at the moment. To the right is the second pointer, and that's the greater than sign there. Then all the nodes with labels that are greater than D0 would be to the right. So if we had nothing but nodes like this, it would be a binary search tree. But that's not how it is. Here's another case of a node. You know where we're going with this. Let me draw the picture of the empty node. Up to 4 kids, up to 3 data values, and we'll graduate up to D0, D1. Two data values. What do we got over here? Well, to the far left, child number 0. And all the way, by the way, these are either garbage or there's no point in initializing them. We'll just say they're garbage, and these are zeros here. Okay, so to the left of D0 are still labels that are less than D0. The second, third child, if we go all the way over here, this is all the labels that are greater than D1. Well, what about that middle child? That middle child also has to be occupied. That's going to point to the subtree that has all the nodes with labels that are between D0 and D1. Now, this is still going to be used in the implementation of a dictionary, so we're still going to disallow duplicate keys. So if you're a little uneasy or a little bit queasy, that, well, what about less than or equal to D0? No. Equal, we threw it out if they tried to insert it. So we'll have to the far left things that are strictly less than D0. In the middle, between D0 and D1, in effect, we've got all the labels, all the nodes with labels that are between D0 and D1, and then the third pointer points to D1 over there. And you probably have gotten way ahead of me in your boredom and filled out the grand finale of the cases of nodes that we could possibly have. Absolutely predictable. We like that, don't we, when things are absolutely predictable. D0, D1, D2. And I bet you got the subtrees filled in already, haven't you? The far left, I'm going to have to do a line to separate these from each other. On the far left, we've still got things that are less than D0. The second one is still things that are between. I'll abbreviate between. Between D0 and D1. The third child has the nodes with labels that are between D1 and D2. And the far right, the fourth child, are the labels of all the internal nodes that are greater than D2. There. From the fairly simple, the equivalent of a binary search tree node, to the wild and crazy. 3 data values, 4 kids. If you were thinking ahead to implementation, the node here is not going to have just a data value and a left and right child pointer. No, we'll have an array, a little miniature array. Now, it doesn't have to be an array. You could just have 3 separate data value variables, but sort of a standard way to facilitate looping through the data values, if there's more than one, is to make those a little miniature array, 3 data values, a little miniature array of 4 child pointers. Now then, I'm going to have to reclaim some board space up here because I want to, oh no, I erased my beautifully handwritten keys up there. I'll have to recopy that before the next video because we're going to use them again. Notes, darn it, I'm sorry that I erased that. I'll switch color for the notes. Maybe that will make me happier. Notes, that's blue. I know these colors are hard to distinguish in the video, but just take my word for it. These are for future reference. I'll even put that because they're not going to make any sense at all right now. For future reference. I can at least spell REF. For future reference. There. Number 1. And why for future reference? Because these are so weird, they're going to look crazy right now. A new data value is always inserted into an existing internal node with no children. I told you they were weird. A new data value is always inserted or put, it's the put operation, into an existing, I-X-I-S-T-I-N-G, existing internal node with no children. Now, implied by the with no children part, that we can understand. With no children means it's at the bottom of the tree. It's one of those nodes at the frontier. One of those that are all across the bottom of our balanced tree. The weird part is, well, where did it come from if it's already existing by the time we get there? We lay plans. You'll see what I'm talking about. This video will make more sense after you watch actual construction of one. But I want to get these notes out of the way just so that we have these to refer to. 2, during an insert operation, or put, same thing. Whenever, this could happen more than once. Whenever we reach a, what I'll call type 3 node from above, how else would we reach it? We're coming down the tree. Of course we're going to reach it from above. Whenever we reach a type 3 node from above, we split it. That, yes, needs some explanation. I'm going to do that with a picture. I'm going to leave type 3 on the board and call that my before picture. You might want to redraw this. Don't mess up your 3 different types of nodes here. But the before picture is this. There is some unseen parent up here, a parent node. And that's a child. It could be the left child, it could be the middle child, right child, whatever. We don't know, we don't care. It's somebody's child, though, in the tree. And this is before. So we're going along our merry way, walking down the tree, trying to find a place to put the new data value. And as we follow this, because it's, let's say it's between 2 data values in the parent node. So we've got to follow whatever pointer is sandwiched between those 2 data values. And we bonk, we hit this one on the head, which is this case right here. During an insert operation or put, whenever we get down to a type 3 node from above, we split it before we go any further. So what's going to happen is, that's the before, here will be the after. The parent's still going to be there, of course. Your parents are always there for you. But this node is going to pop. It's full. I can't put any more data in there. I don't have any space for the thing that's trying to be inserted. So it splits into 2 of these big, crazy looking nodes where D0 is alone in the first of the 2 pieces that it splits into. And D2 is alone. Now notice, when there's only 1 data value filled in, it's always got to be the first one. If there are only 2 data values filled in, it's got to be the first 2. And if there are 3, then it's all maxed out. We don't have to worry who's which. Now then, here's the weird thing here. When they split up from each other, they also divide the kids. Over here, I will have the things that are strictly less than D0. This will be still the things that were between D0 and D1. In other words, it keeps these 2 subtrees, whatever they are. These are 2 subtrees. I could have called those and probably should have T0 and T1. This keeps subtrees T0 and T1 for itself. This one takes the other 2 kids, which would be T sub, you know what, I'm going to come back with a different color and put those, because it's probably easier and cleaner to think of these as subtrees rather than what's between what. But this is the subtree that has everything that's between D1 and D2. And the second pointer now is everything that's greater than D2. Yeah, that needs relabeling. This is subtree, capital T sub 0, capital T sub 1, capital T sub 2, capital T sub 3. Now we can just think of those positionally and not worry about how the data values got there. So T0 is this one over here. On the far left, this node takes kids T0 and T1. This one takes nodes T2 and T3. And both of these are children of the same parent. We've got the same parent node, but now it's got an additional kid. That's going to need some discussion. That's not even the weirdest part. Who's missing here? D1. D1 moves back in with the folks. D1 rises up from this child node of type 3, which the 3 doesn't make any difference now. That's purely a before picture for this split operation. The D1 rises up and moves back in to the basement bedroom of the parents up here. How can that be? How do we know there's going to be room? Well, this is a recursive descent. If we had reached the parent, and the parent had been full as a tick, with all the data filled in and all the pointers filled in and everything, we would have split that on the way down. That's what I mean. We might have to split more than once on the way down. What we're doing is making space for any kid that has to move back in with the parent. And we're also going to have space for the new data value. When we get to the bottom of the tree and there are not any kids down here, then there'll be 2 places the new data could go here, 2 places the new data could go there. That's way ahead of the game. Let's just talk about the mechanics of this operation. If I reach a full jam-packed node, no more space for data, no more space for children, then before I go even one step further, before I even follow this pointer and come down to this node, I split it. This middle data value will move in with the parent and become one of its 3 data values, which we know we have room for because there's not any possibility it would still have 3. It itself would have been split on the way down the tree. It's also going to have room for an additional child pointer to be filled in. Since it doesn't have 3 data values filled in, it doesn't have all 4 of the child pointers filled in. The only way all 4 of the child pointers could be filled in is if all 3 of the data values are filled in. And we know that's not the case with the parent. Now, where this goes, this is not necessarily the first 2 kids. It could be the last 2 kids. It could be anything in between. Where they go doesn't matter. We just know that there is going to be space. And now we've opened up 2 places for data values here, 2 places for data values there. Does this make any sense? I'm going to guess no. So put all this in your notes so that you can refer to it in the next video, also known as video 31, when we try this again. Let's try inserting those again in this wild and crazy new type of tree that we've got. Okay, I'll see you online.